Swayam Prabha. Digital India. Educated India.
We have been discussing some topics about virtual memory over the last few lectures. Now, in this last lecture of the module, we shall be discussing a few other aspects of virtual memory, and then we shall be moving over to the next module. Now, if you recall, whatever we have discussed so far, we have discussed the notion of demand paging specifically. We looked at the various page replacement algorithms. We discussed the impact of the page fault and other things. So, these are a few things that we have studied in some detail. Now, let us look at a few other things. See, we talked about locality of reference. Let us look at locality of reference from a slightly different perspective. Okay? So, let us start this lecture today by talking about something called the working set model. Before going into this, let us try to explain what do you mean by working set and how this model helps us in the context of virtual memory. Let us see. Now, let us first try to define the working set. What is a working set? See, working set is essentially a set of pages, or you can say a set of page frames in memory. Okay. So, how do you define a working set? Very loosely, you can define the working set, of course, with respect to a process, because working set will vary from one process to another. Working set of a particular process is defined as the set of pages, of course, in memory, which defines the locality. Now, locality, if you look at the concept of locality again, if you think what we discussed earlier with respect to locality of reference, we talked about spatial locality, we talked about temporal locality. We said that when a process is executing, there are certain number of pages which are accessed very frequently. Now, the set of pages that are accessed very frequently, that can go on changing with time. Let us say initially one loop of the program was executing, so certain pages were being referenced during that time. Later on, when the program advanced, some other loop might be executing, so there some other pages might be accessed frequently. So, the locality that we are defining as the set of pages that are accessed frequently, that can change over time. Okay? It is not something fixed. So, working set is nothing but that locality that we are capturing, the set of pages that are mostly accessed by a process at a given point in time, that is defined as the working set at that point in time. Okay? So, it is clearly mentioned here, the working set, the way we define, is a function of time, it changes with time. So, what is the intuitive reasoning here? Now, I am repeating, locality means the set of pages that a process is currently requiring very frequently, that is the locality. Now, you see, if you are able to allocate enough frames to a process, suppose the locality of a process consists of 5 pages. So, if I have allocated already 5 or more pages, then the entire locality can be accommodated in memory, you can load all the required pages in memory. But if you allocate less number of pages, you cannot load the entire locality, and when those pages are accessed frequently, there can be thrashing, lot of page faults might happen. Okay? So, the idea is that if you are able to allocate enough frames to the process to accommodate its current locality, the set of pages that it is accessing frequently right now, then there will be very less number of page faults. Page faults will start to happen only when the process moves from one locality to the next. One locality to the next means another part of the program where some other pages are getting accessed. So, only during that time there will be faults, otherwise there will be very less number of page faults. However, if we do not allocate enough number of pages, if the number of allocated frames, page frames are less than the size of the locality of the process, then there will be lot of page faults, because those are the pages which are accessed frequently and you are not able to load all of them in memory. So, thrashing will take place. So, the idea is that if you can accommodate the working set of a process in memory, then there is less likelihood of thrashing to occur, otherwise there may be thrashing. So, intuitively what we want is that we want to always try to keep the working set of a process in memory. If we can do that, possibly the number of page faults will become less. Okay? That is our justification. Now, let us slightly mathematically try to work it out. So, we define something called a working set window, and let us denote it by capital delta. So, working set window is nothing but a set of page references. See, when a page is let us say when a process is running, a sequence of pages will be accessed. So, earlier when we discussed the page replacement algorithm, we talked about the page reference string. So, here we are talking about the page reference string. So, suppose I have a very long page reference string. Out of that, if I take any window of size delta, delta can be anything, let us say 10,000 references. So, within the 10,000 references, whatever pages are accessed, that will be contained in the working set window. So, delta will contain all set of pages that are within this 10,000 references, right. That is how we define the working set window. Now, working set, of course, this working set window will vary from one process to another. So, if we denote it by WSS, WSS of process I, this is the working set of process PI. So, as I said, we define it as the total number of pages referenced in the most recent delta references. So, earlier we said delta is 10,000. So, as I said, when a program executes, it moves from one locality to another. So, obviously, this WSSI is a function of time. Of course, the choice of delta is important. We are essentially what we are trying to do, we are seeing that we are looking at a window of size delta and we are observing what are the pages that are contained in that window. We are trying to keep all those pages in memory. Now, if we find that the choice that we have made for delta is too small, let us say we have taken delta equal to let us say 1000 or 2000, which is not enough, it cannot capture the whole locality. So, if delta is too small, we cannot capture the entire locality and the set of pages you are loading may not be enough, there can be page faults very soon. So, it may not encompass the entire locality. On the other hand, if you choose delta to be too large, let us say I take delta to be 1 lakh, 10 lakhs, then it is so large that within that window multiple localities can get included. So, unnecessarily we are trying to load too many pages which may not be required at any given point in time. So, it may encompass several localities, and in the extreme case if delta is very large, let us say infinite, which means it will encompass the entire program. All the pages that are being accessed in the program, delta will include all of them. Now, if we take the sum total of WSS of all the processes that are running, WSS I is the number of pages required for process I. So, if you do a sum total, you can get a total demand of frames by all the processes running in the system. So, you can get some idea that what is the total demand of all the processes in the memory. So, you can decide that whether you can accommodate more number of processes or you should swap out some of the processes from memory. Okay. So, let us look at this pictorially whatever I have said. Let us say we have allocated m number of page frames to a process. If the value of demand of a particular process, let us say, is greater than m, it may lead to thrashing. So, if thrashing occurs, then we may have to swap out some of the processes from memory. Let us take a small example. Let us take this page reference string as is shown in the top 26157777 and so on, and we look at a sample value of delta. This is my working set window. This encompasses 10 memory references. Now, you see in this first 10 memory references, if you look at this page reference string, the set of pages that are included are 1, 2, 5, 6 and 7. There are 5 pages which are being accessed in this window, and this delta moves in the axis of time as the instructions get executed. Let us say sometime later we have the value of delta here, which is this set of pages. So, you see here only 2 pages are being accessed, 3 and 4. So, this is what I said, that the set of pages that are being accessed within this interval delta can vary with time. As delta moves, slides along this page reference string, the value of the working set or the content of the working set can also change. So, as I said, working set is a function of time, working set at T1, working set at T2 and so on. Okay? Fine. Now, the next question is, suppose in an operating system I want to implement this concept of working set. So, if I could somehow keep track of the working set, then I know that which are the pages I should keep in memory. So, the question is, how should I keep track of the working set? Okay? Let us see that. Now, exactly keeping track of the working set may be too expensive. So, what we propose here, this method is some kind of an approximation. We try to approximately keep track of the working set. How we do it? We need 2 things. One, we need a timer. So, what does the timer do? I load it with some initial value. So, with every clock the value of the timer decreases. As soon as the timer reaches 0, it generates an interrupt. And reference bit. Now, reference bit, I am initially talking about one reference bit, but in general there can be multiple reference bits. Okay? So, reference bits along with every page. So, when we talk of the page table again here, if you talk of the page table, so conceptually along with every entry in the page table, we will be having a set of reference bits. This is the additional thing that we need. Let us take an example. Suppose we choose a window size of 10,000. So, we want to estimate what are the pages that are accessed within this interval 10,000. And let us say we set the timer in such a way that an interrupt is generated every 5,000 time ticks. Every 5,000 references interrupt is generated, and we use 2 reference bits in every page. Okay. So, you try to understand what you are doing. Whenever the timer interrupt, you see there are 2 sets of reference bits. If I treat them as 2 columns, this is the first set of reference bits, second set of reference bits. Let us say initially they are all initialized to zeros. The idea is that whenever a page is referenced, the corresponding bit is automatically set to 1, like this. So, whenever there is a timer interrupt, what I do? I copy this second bit string into the first bit string. and after copying I check what are the bits that are non-zero. If the bits are non-zero, those pages are in the working set. You see, so after copying I reset these to 0, these two all zeros again. So at any point in time whenever a timer interrupt comes, there are two vectors, right. One is the copied vector in the previous time, one is the current vector which have been modified. Now here I check, if I check these two bits are not all 0, if there are both zeros, which means over the last 10,000 time none of these bits are 0, mean both are 0 means they are not, this page was not accessed. But if it is either 0 1, 1 0 or 1 1, which means this page was accessed. So any non-zero value of the reference bits will indicate that the page should be in the working set. Now just one point to note is that how many reference bits we have to keep, that means whether two vectors or multiple vectors, like a shift register. So I am saying they will have to be copied. So it is like a shift register, just you shift once, the second vector will get copied to the first vector. So there can be multiple such vectors, like let us say instead of 10,000, instead of 5,002 reference bits, I can choose to have 1,000. I set the timer to interrupt at 1,000, every 1,000, and I use 10 reference bits. So there I can get more accuracy, I can get a resolution of 1000 time units. So I can resolve if a locality is less than 10,000, that also can be identified. So this is just a trade off, how many reference bits you have to keep track of the working set. Okay. So essentially what I am saying is that there will be these kind of bit streams. So I talked about 2, let us say there are 3, let us say there are 3. So there will be entries and these entries correspond to the pages, the logical pages. Let us say this is page number 0, page number 1, page number 2 and so on. And this is organized like a shift register. So you can shift them. So as I said, every time a timer interrupt comes, there will be a shift, you reset the last one to all zeros and you start the process. So in this last register, some of the zeros will be changed to 1 whenever there is a page reference. And at any point, to identify whether a page belongs to the working set or not, you see all the 3 bits. You see all the 3 bits whether they are all 0 or not. If they are all 0, you can deduce that it is not in the working set, not in the locality, otherwise it is in the locality. Okay? Fine. Now instead of working set, we can have a more direct approach. See, ultimately what we are trying to do, why we discussed working set, we want to decide or want to know what are the pages we need to keep in memory, so that thrashing can be controlled. We do not have thrashing, but we can have a more direct approach. So how we do that? We means the operating system can keep track of the page fault frequency. Page fault frequency means number of page faults per unit time. Number of page faults per unit time. See, unit time can be any time unit. Let us say in every means every 1000 references, how many page faults are there? That can be the page fault frequency. And another thing is assumed in this method, that every process uses local page replacement policy. You recall we discussed this earlier. Local page replacement means for a process, let us say PI, certain number of pages are allocated. So while PI is executing, if there is a page fault and you need to select a victim page for removal, one of those pages will have to be removed. So PI will not take away pages from another process PJ, that will never happen. Okay? So all page replacement will happen from its own allocated frames. that is mentioned here. The victim page is selected among one of the allocated frames of the same process. Now, the operating system keeps track of the page fault frequency, because every time a page fault occurs, some counter is incremented in memory. Now, there can be two cases. Operating system may see that the page fault rate is too low, which means there is no thrashing. So, operating system can assume that the process may not be requiring all the frames that are allocated. So, why not take away some of the frames, and let us see if still the same thing remains. So, then unnecessary, I do not have to allocate frames to that process, I can give those frames to some other process who needs it. In the second case, it can find that the page fault rate is too high, which means maybe the page has not been allocated enough number of pages to encompass its locality. So, it should allocate more number of pages. Page fault rate is too high, allocate more number of page frames. It is simple. You simply keep track of the page fault rate, maintain some thresholds. If it is below some threshold, take away some page frames from that process. If it is above some threshold, allocate some more page frames to that process. Okay. So, this works well, and many operating systems implement this kind of simple technique. Pictorially, this is depicted like this. So, with respect to the page fault rate, there are two thresholds which are pre-decided, upper threshold and lower threshold. So, if at any point in time it finds that the number of page faults is exceeding the upper bound, then you increase the number of frames, allocate more frames. But if it is less than the lower bound, then you decrease number of frames. But if it is in between, it is fine, do not do anything, that is the normal range. Okay. So, this is a simple method which works well for most of the operating systems. Okay. Now, this working set and this page fault rate, they have some kind of a relationship. Let us see. You see, look at this diagram below. Here, for a typical process, we are plotting the page fault rate versus time. You see that some points in time page fault rates are higher, peak, then it is again low, then again it is high, again low, again it is high. So, you see over a period of time there are certain periods when the process may be requiring more number of pages and the page fault rate is increasing. So, again with respect to the working set, in the previous model we had defined a fixed value of delta. Let us say this was my working set. Now, working set is not that accurate because I am fixing delta arbitrarily, right. Now, delta may include this period where there is more number of page faults, also it can include that part where there is very less number of page faults. So, I am more interested in this part where there is a peak, number of page fault is suddenly increasing. So, the direct method of using page fault frequency may work better, right. This is what I want to say. Okay. Another very interesting thing let us talk about. Suppose I write a program and I run it on a machine. Okay. While running there can be certain number of page faults. Now, as you know, the same program can be written in so many ways. If I write the program in a slightly different way, it may so happen that the number of page faults can significantly differ. So, let us take a very simple example, but also an extreme example. Let us use C-like notation. Suppose we declare a 2-dimensional array like this, a 128 by 128 2-dimensional integer array. just a small change, this name should be data, okay, data, okay. So, a 2-dimensional array called data 128 by 128, and we assume that in memory. So, you know, in memory we have the pages, the page frames, they are the page frames. Suppose these page frames are large enough so that they can store one row in every page. So, one row means let us say 128, let us say every integer requires 4 bytes. So, I am actually talking about 512 bytes. So, I am assuming every page size of every page frame is 512 bytes, and also I assume that the array is stored in memory in row wise fashion, first row number 0, row number 1, row number 2, like that. Suppose I want to write a small program which wants to initialize, which will be initializing this entire array to all zeros. So, there are two versions of programs I am showing here. In the first one, the j loop is first and I is the inner loop. In the second one, I is the outer loop, j is the inner loop. So, in the first program, you see, for j equal to 0, the entire I loop is getting executed. So, you are accessing the elements column wise, first column, then j equal to 1, entire I loop, second column, third column. In the first version of the program, you are accessing the elements of the array column wise, but in the second version I is outside, I is 0, entire j loop is inside. So, I 0, 0, 0, 1, 0, 2, so row. So, here elements are accessed row wise. So, you see in the second version of the program, once you bring in a data page, the first row of the array, all the elements will be accessed one after the other, then only the second row will be brought, access one after the other, then the third row, then the fourth row. So, there will be total of 128 page faults, because there are 128 rows. But in the first case, you are accessing them column wise. So, for every column you will be accessing all the rows. So, you will have to bring the rows 128 times for every column. For the second column again 128 times, 128 times. For third column again 128 times. So, you will be needing 128 multiplied by 128, 16,000 odd page faults. So, you see, a small change in the program can drastically change the performance of your execution. So, when you are writing a program, it makes sense to know how things are allocated in memory, how arrays are allocated in memory. So, you can also write the program in a way that will incur less number of page references. Of course, compilers try to do some optimizations, but it is always good as a user you also understand this and follow this kind of a principle. Okay? Fine. Now, let us now look at another thing. See, earlier we talked about the page table. We said that we have a logical address, page number and offset. The page number is used to index into a page table. But what if I have a very large virtual address space and the size of the page table becomes very large? How do I store the page table? Should I store it in a contiguous area in memory? Is it possible to store such a large table? Let us discuss this. So, what I am saying is that for large logical address space, size of the page table can become huge. Let us take some examples. Consider a moderate size of logical address space in many of the modern day computer system, let us say 32-bit logical address. Now, in fact, many of the modern day system they use 48 bits, 64 bits, even larger than this. So, let us take 32 bits to start with. Realistically, let us assume that we have pages of size 4 kilobytes. 4 kilobyte means 2 to the power 12. Okay. So, this 32-bit logical address space, so if you split it up, you will find that you will be needing 12 bits for page offset. For the offset you will be needing 12 bits and the remaining 20 bits for the page number. So, this will be your page number, this will be your offset D. Now, 20 bits for the page number means there will be 2 to the power 20 possible pages. So, if you store the whole page table, there will be 1,000,000 entries, and assuming every page table entry requires 4 bytes, which means you are saying your page table size will be 4 megabytes. Normally, for fast access, page table needs to be stored in contiguous place in memory, but getting a 4 megabyte contiguous space in memory may be difficult. So, the question is, how do I store the page table then? The way page tables are stored in modern day computer system is that instead of storing it as a single unit, you store it in the form of a hierarchical fashion. You divide the page table into smaller units, where each of the unit can fit into a page. So, page table itself is paged. Instead of storing in a contiguous place, you put parts of the page table in different pages in memory. That makes your memory management also very uniform. Okay? Let us see. Let us consider a so called 2-level page table. We are showing a 2-level page table. So, what I was saying is that logical address, let us say initially we had 2 parts, right. There were 12 bits in the offset and 20 bits in the page number. Now, you are saying the page number part we are dividing again into 2 parts, let us say 10 and 10. This is first level page table, let us call it P1, second level page P2. So, these 2 page tables are called outer page table and inner page table. The idea is as follows: this page number we are dividing up into a 2 tuple P1 and P2. Okay. There is a outer page table as this diagram shows. You use P1 to access this outer page table. Because P1 is only 10 bits, the number of entries in this table will be 2 to the power 10, which is equal to 1024, approximately 1000. And this entries in this outer level page table will point to another small page table that will be indexed by P2. For example, you go to this page table. Now, here you use P2 to select one of the entries. So, depending on P1, this is the second level page table, this is sometimes also called inner page table, okay, inner page table also. So, depending on the outer page table access, you select one of the inner page tables, and the inner page table is getting accessed by P2, okay, and by accessing you get the final frame number. So, the only thing is that instead of one memory access to access the page table, here you will be requiring 2 memory accesses, one memory access for the outer page table, one memory access for the inner page table. Okay. So, that same example let us continue. So, I said 32-bit logical address with 4K page sizes, this is the example we are taking. So, page number was 20 bits and offset D was 12 bits, this is what I said, D is 12 bits. Now, we divide them into 2 parts P1 and P2, each of 10 bits and 10 bits. This is exactly what I said, P1 will be 10 bits, P2 will be 10 bits. Now, you see there will be 2 to the power 10 entries in the table, right, page table. Now, each page table, if I assume each page table entry is 4 bytes, so the size will still remain 4 kilobytes, the same as a page, because with 12-bit offset we are assuming the page size is 4 kilobytes. So, our page size still remains 4 kilobytes, 2 to the power 10 entries, each entry of 4 bytes. Okay. So, it is consistent with the page size. Okay. Now, address translation scheme, pictorially it is shown here. So, when the CPU generates a logical address, the first 10 bits, which is P1, is used along with the page table base register. You know, page table base register points to the starting address of the page table in memory. It will give where the outer page table is, and the outer page table will give you the address of one of the inner page tables, and that will be combined with P2, that which offset there. So, you will be getting some offset here, from there you get the frame number F, and finally, the physical address is determined and you access main memory. Instead of single level access, we have 2 levels now. Okay? This is how it is done. Now, if the address size is even larger, let us say 64 bits, then if you simply make a division, let us say 4 kilobyte page size, so offset D will be 12 bits and the page number now will become 52 bits, very large, 2 to the power 52 entries, extremely large. So, even with 2 level page table, the pages will become very large. So, 2 levels will not be sufficient, you need multi level page tables now. So, this 52 bits, even if you divide into 10 and 42, still the outer page table will be needing 2 to the power 42 entries, huge. So, you need 3 or 4 levels, you have to divide up in a similar way into 3 or 4 different levels. This is how it will work. Okay? Let us pictorially see one 3 level example. Let us say, this of course a slightly different example, not the same one. Here we assume our offset D is 20 bits, D is 20 bits, which means page size is 2 to the power 20. To the power 20 means 1 megabyte size pages, and the remaining bits 64 was total. So, remaining 44 bits we divide into, let us say 8, 18 and 18. So, 8 bits will be used to access the outer page table, there will be 2 to the power 8 entries. Next 18 bits will be used to access one of the pages in the outer page table 1 or inner page table 1, whatever you say. So, here there will be 2 to the power 18 entries, and assuming 4 bytes per entry, it will be 2 to the power 20. So, same means 1 megabyte size. Okay. Similarly, from here you access another inner page table, and then you create the final memory address by getting the frame number. So, you can split it up. So, here there will be 3 memory accesses required to access the page table. So, if we have multi-level page table, the only price you are paying is that the access time of the page table, in case you do not find it in TLB, access time will become larger, either 2 accesses or 3 accesses, and finally you will have to access memory after that. Okay? Fine. Now, lastly, you see in the beginning we said that broadly we have 2 approaches, paging and segmentation. Let us just give a very brief idea what segmentation really means. I shall not be going into the detail of segmentation here. Segmentation is a memory management technique just like paging, but in paging you recall we are dividing the logical address space into equal sized pieces, but here we are dividing the logical address space into variable size segments. Not only that, these segments are something which are user visible. See, when you divide something into pages, those are not understood by the user, that which page corresponds to which part of the program. But in case of segments, user can say that, well, this is my main function, this is a subroutine, this is my stack, this is my data area, these will be the segments. So, those are user level entities. Okay? So, what I am saying is that each segment is a logical unit of a program or a process, like different parts of the code, main function, subroutines, stack, error handler, data, different. Okay? And information about the segments, just like you have page table for paging, they will be stored in something called a segment table, which will tell you in memory where exactly a segment is located. So, for contiguous allocation, recall we used a base register to indicate the starting address, we use a limit register to indicate the size of the segment. So, similarly, every entry of the segment table will contain base and limit values in addition to other information like access. Some segment may be read only, some segment can be read write. Now, in general, we can also combine segmentation with paging. In the first level, we can have segments, and every segment in turn can be divided into pages. So, you can combine segmentation with demand paging. That many of the modern architectures do support this kind of a hybrid architecture. Okay. So, pictorially let us try to explain that how this segmentation works. Let us assume on the left we have a process, a program 1. The logical address space, this is user visible. You can treat it as 3 different segments. First segment can be a main program, a main function. Second segment can be a subroutine 1. Third segment can be a subroutine 2. As you can see, main has a size of 500, 0 to 499. Sub 1, 0 to 199 has a size of 200, and segment 1, 0 to 99 has a size of 100. And on the right side you have your physical memory, the main memory. So, you see that your main is loaded somewhere in memory, sub 1 is loaded somewhere in memory, and sub 2 is loaded somewhere in memory. So, if you look at the memory addresses, you will see that sufficient memory is allocated for 500 bytes, 200 bytes and 100 bytes. In the middle, you will be having the segment table, you can say segment map table, different names are followed. So, as I said, the most important things are base and limit values. For every address that is generated, the starting address of that segment in memory, let us say for the first one, starting address is 3000 and size of that segment is 500. And access type is also mentioned, as I said, this is an executable, you cannot write into it, you can only execute. But if it is a data segment, you can have read write access, right. Now, actually what will happen, as you know already, that whenever CPU is generating a logical address, first the value of the logical address will get added with the value of the base register. Then of course, you check for the limit, right. So, limit you can check before whether the value of LA is less than, that means you will have to check whether this LA logical address which is there is less than limit or not. If less than limit it is not there, then only you do this addition, as I mentioned, addition with the base, you get the physical address. This was discussed earlier already when we talked about contiguous allocation. Now, in basic segmentation we do something similar, but there are multiple segments in the segment register. Now, as I said, many of the modern day computer architecture like the Intel series of processors, they follow this kind of segmentation concept. Of course, there is another level, demand paging is also there after that, but segmentation is at the higher level. And when you write a code at the assembly code level, you can identify your segments in a program, you can define your segments, stack segment, code segment, data segment, extra segment and so on. So, with this we come to the end of our discussion on memory management and virtual memory in general. So, we discussed the various kinds of techniques, some of them we discussed in some level of detail. Now, in any real system, if you look at, you will find that some variation of these methods are only used. So, later on when we shall be looking at some specific case study, we shall be seeing how, for example, under Linux, how an Intel machine, how it is managed, the memory is managed there, what kind of pages are used and so on. So, all these things we shall be discussing later when we talk about the specific case studies. Okay. So, in the next module, we shall be looking into file systems, how files are stored in secondary storage, what are the different kinds of file system organization, how directories are stored, how data are stored and so on. So, all these things we shall be discussing starting from the next lecture. Thank you.